In software development, we model complex systems within code. Traditional paradigms focused on step-by-step instructions leading to intricate code bases. Object-oriented programming, or OOP, shifts the focus to data and their interactions. Imagine assembling a car with a massive list of instructions. OOP offers a more intuitive alternative. Think in terms of objects, the car, the engine, the wheels, and their interactions. This mirrors how we perceive the world, making design more natural. OOP provides principles for organizing and structuring code. Encapsulating data and behavior within objects creates modular, reusable components. This shift empowers developers to tackle complexity with ease. Central to OOP are classes and objects. Think of a class as a blueprint defining the structure and behavior of objects. For instance, the car class outlines properties like color, model, and engine size. It also specifies actions like accelerating, braking, and turning. An object is an instance of a class, a concrete realization. Your car, with its specific attributes, is an object. Similarly, your friend's car is a distinct object of the same class. Classes provide the framework, while objects populate our programs. Within a class definition, we encounter two key elements: attributes and methods. Attributes represent the data associated with an object, its characteristics or properties. In our car class, attributes might include color, model, engine size, and fuel level. These attributes store the specific values that differentiate one car object from another. Methods, on the other hand, define the actions an object can perform, its behaviors or functions. For our car class, methods could include accelerate, brake, turn left, and refuel. These methods encapsulate the logic for how a car performs these actions, taking into account its current state and attributes. Attributes and methods work in tandem to provide a complete representation of an object. Attributes store the object's state, while methods define how that state can be manipulated or accessed. This interplay between data and behavior is a defining characteristic of OOP, allowing us to model complex interactions in a clear and concise manner. Section 4. Encapsulation. Safeguarding complexity, promoting clarity. Encapsulation is a cornerstone of OOP, bundling data and methods within an object. It shields internal complexities, exposing only a controlled interface. Imagine the car object. The engine's workings are hidden from the driver. The driver uses a defined interface: steering wheel, pedals, and controls. Encapsulation ensures the driver doesn't need to understand the engine. It offers significant advantages in software development. By hiding details, it reduces dependencies and promotes modularity. Section 5. Inheritance, building upon existing foundations. Inheritance, another powerful concept in OOP, enables us to create new classes based on existing ones, inheriting their attributes and methods. This mechanism promotes code reuse and reduces redundancy, allowing us to model hierarchical relationships between objects. Consider a specialized type of car, such as a sports car. Instead of redefining all the attributes and methods common to all cars, we can create the sports car class as a subclass of car. The sports car class would inherit all the properties of its parent class while also introducing its own specialized attributes, such as turbocharged or spoiler, and methods like engage sport mode. Inheritance allows us to build upon existing code, extending functionality without rewriting everything from scratch. This hierarchical structure mirrors the way we categorize objects in the real world, making our code more organized, intuitive, and easier to maintain. Section 6. Conclusion, the power of objects, reusability, maintainability, and beyond. Object-oriented programming, with its emphasis on objects, classes, encapsulation, and inheritance, offers a powerful and flexible paradigm for software development. By modeling systems as interacting objects, we gain numerous advantages. Code reusability stands out as a major benefit. Well-designed classes can be reused across different parts of a project or even in entirely separate projects, saving time and effort. Maintainability also improves significantly. Encapsulation ensures that changes within one object have minimal impact on others, making it easier to modify and extend code without introducing bugs. Moreover, OOP promotes a more natural and intuitive way of thinking about software design. By modeling real-world entities and their interactions, we can create code that is easier to understand, debug, and maintain. As software projects grow in size and complexity, the principles of OOP become increasingly valuable, allowing developers to build robust, scalable, and maintainable systems.